Hi, my name is Adam Rhodes and I'm a thermal engineer at Optimized Thermal Systems. Today I'll be doing a quick demo of VapCyc. VapCyc is a vapor compression modeling software developed at the University of Maryland. To get started, I'll start talking about the interface of VapCyc. In the center here you see the graphical interface of your current cycle. Right now we are showing a basic 4-component cycle with a condenser, an evaporator, a compressor, and an expansion device. If you right-click on any of these icons, you get a list of options. The main options here are Choose Component or Edit Component. Clicking Choose Component brings up a list of models of this component included with VapCyc. Selecting any model brings up the Edit Component window, which allows you to edit any of the parameters of this model and save it. On the left, we have the System window, which lists all of the components currently in the cycle. Similar to the graphical interface, you can right-click and select Choose Component or Edit Component. The General tab shows us the current file name of the file you are working with, and an area that allows you to enter notes or a description for your current project. In the bottom left, we have the Component Properties window, which shows parameters for each component in your system. Clicking on the button next to any of these names brings up the Edit Component window for that component. The Fluid Properties tab allows you to calculate air and refrigerant properties. For the air side, we can enter temperature, pressure, and relative humidity, or temperature, pressure, and wet bulb temperature, and calculate the density and dew point and humidity ratio of the air. On the refrigerant side, we can calculate the saturation properties of the refrigerant. We can enter saturation pressure or saturation temperature and calculate the bubble and dew pressure, bubble and dew temperature, and liquid and vapor enthalpy. In the bottom, we have the Details window, which shares information about the currently selected component, including the name, class, and file of this component. We also have the Error Messages tab, which shows the current errors for your cycle, and the component warnings to show current warnings. To run a simulation, you click the play button, and once the simulation is complete, a results window appears. This window shows the bulk system properties of the simulation, including COP, capacity, power consumption, and charge. It also shows the system state points at each junction. The numbered junctions refer to the numbers on the graphical interface. In addition to the bulk results, we can look at the results for each individual component. Here we see the results for the evaporator, including the inlet and outlet refrigerant state and the exit air temperature. On the right, we see a breakdown of the charge in the system. Here, the majority of the charge is stored in the condenser. We also have charts to show the 4 state points on a pH diagram. In order to set up your simulation, you need to select your components. To do so, you right-click, select Choose Component, and then choose from the list of components included with VapCyc. For heat exchangers, we have a variety of components included. We have generic heat exchangers, which deal in bulk properties, including tube length, inner tube diameter, number of parallel tubes, air inlet state, and fin efficiency and fin ratio. You also must enter here the tube and fin material density and the heat transfer coefficients on the air and refrigerant side. If you want a pre-sized heat exchanger for a specific size of system, you can choose pre-sized capacity and choose from the drop-down that fits with your expected capacity. In addition to the generic heat exchanger, we also have the ideal heat exchanger. Here we just need to enter the mean saturation temperature or dew point temperature or the pressure of the heat exchanger. We can specify the saturation temperature drop and the level of superheat or subcooling for our heat exchanger. Another generic heat exchanger is the constant heat load heat exchanger. In this case, we are directly entering the expected heat load of this heat exchanger and the expected outlet saturation delta. In addition to the generic heat exchanger models, we also have highly detailed models based on Coil Designer. For this model, you would open up Coil Designer, which is a heat exchanger modeling software, develop your coil, including tube parameters, tube circuitry, and save the file as a CHX file. Then come into VapCyc, choose Coil Designer Reader component, and browse for your CHX file. Once you pick your file, the tube parameters will load in. Tube, fin, air inlet conditions, and any correction factors will load into this component window. And you'll have the option of modifying these parameters as needed. If you'd like to reset back to the file parameters, you can click Reset. If you make any modifications and want to save it as a new file, you can click Save and save as a new CHX file. This allows you to focus on one heat exchanger at a time, develop it in Coil Designer, validate it, and then bring it into a full system model in VapCyc. In addition to the Coil Designer Reader component, which supports tube, fin, and microchannel heat exchangers, we also have a Coil Designer tube-in-tube heat exchanger reader. This supports the tube-in-tube heat exchanger model in Coil Designer. So in this case, you would develop a tube-in-tube heat exchanger model and specify the tube length, the tube diameters, and the inlet state for the secondary fluid. Save your file as a tube-in-tube heat exchanger file. And then in VapCyc, load it in. Here I'll choose from the Coil Designer pre-made samples, which are included in the installation path. Again, here we are loading in the parameters from the saved file. We can edit them as needed. In addition to the Coil Designer Reader components, we also have components that are specific to a single heat exchanger manufacturer. Here we can look at a heat exchanger specifically for SWEP brazed plate heat exchangers. Here we are working with a selection software directly from SWEP, and we can select from their catalog of heat exchangers based on a certain filtering mechanism that we have set up here for condenser, condenser dual type, or condenser heat pump. We have multiple heat exchanger models based on specific manufacturers' heat exchangers, and we're adding more every year. So that's all the heat exchanger models for the most part. Moving on to the compressor, sorry. For the compressor, we have generic physics-based models, map-based models, and two-stage models. For the generic models, we can specify a displacement for the compressor, the efficiencies of the compressor, and the RPM of the compressor. We also have pre-sized capacities for different levels of system. In addition to this generic heat compressor, we also have generic compressors with shell heat transfer. These require a bit more information about the heat transfer area of the inside and outside of the shell, also the heat transfer coefficient of the inside and outside of the shell. But this model calculates the amount of heat loss through the shell of the compressor. In addition to these generic models, we have map-based models. Here I'll show the latest 10 coefficient database compressor model. This map-based model is based on the AHRI 10 coefficient polynomial for modeling compressor performance. This model is reliant on a database of compressor coefficients that provide the mass flow rate and power consumption of the compressor in VapCyc. We provide a template for developing your own database of compressors. Here I'll show the Excel version of this database. There is also a Microsoft Access version of this. In this database of compressors, you can specify the manufacturer and model name of each compressor, as well as some identifying information for this compressor. On the right here, we have all the coefficients as specified by AHRI standard 540. Here we have the capacity coefficients, the power consumption coefficients, the amperage coefficients, and the mass flow rate coefficients. So once you get these from the manufacturer or calculate them yourselves from performance data, you can enter them into a database, save this database, and then load it into VapCyc. We have a number of pre-made template databases available here for you to work from. Loading in this database brings in all of the compressors listed in the Excel model. You can click on one of the compressors to select it and use its performance, or we can filter based on the model name. You can also filter by the refrigerant of the compressor or the application type, such as air conditioning. In addition to these filtering options, we also have the ability to set a motor efficiency, which adds a level of heat loss of the compressor. We can also add a mass flow rate or power correction factor. In addition to this, we have a superheat correction factor in case the superheat is not exactly the same as the AHRI standard. In this model, we also have the option of entering a evaporator and condensing temperature and calculating the performance. In addition to the map-based models, we also have two-stage models. In this case, we have a generic two-stage compressor model. This is similar to the generic model, but there is a low stage and a high stage compressor. Here you are setting the displacement, efficiencies, and RPMs of each compressor. You also have the option of setting an intercooler for this compressor, and you have a number of different parameters for this intercooler. So that's the compressors. Moving on, we can look at the expansion devices. In this list, we have a few expansion devices, including a generic orifice valve. Here you can just set a valve diameter, and the mass flow rate, the pressure drop will be calculated. You can also select a precise capacity valve similar to the other generic models. In addition to this, we also have an adiabatic capillary tube model. Here you must select a correlation for the mass flow rate and set a diameter and tube length for this capillary tube. We also have a TXV model. This requires a good deal of information, including the valve coefficient, the reserve capacity, and the high and low side settings. So that's a quick rundown of the main components of the system. We do support the ability to add your own custom components, and there is a template for that and some details of that in the help file. So once your components have been selected, the next thing you need to do before running a successful simulation is set your system properties. So to do that, you go to Edit and then Edit System Parameters. And here you have a list of different options that you need to set. Make sure it's set correctly. For the VapCyc solver settings, for the most part, you can leave this as it is. By default, the component boundary type is set to be the mass flow rate. So in this case, we use the marching solver, and the outlet state of each heat exchanger is calculated from the inlet condition and the current mass flow rate. There's also a pressure option, which calculates the mass flow rate from the inlet condition and the outlet pressure. We also have an option for a default or an accelerated procedure. Default procedure is a bit slower, but has a higher chance of convergence. One important criteria for a successful simulation is setting the right convergence criteria. What this is basically a goal for the solver to reach. So this is a bit more information that allows the solver to reach a converged solution. So in this case, we are telling the solver that we want a charge of 1.1 pounds, and we want the expansion device model to help calculate the low side conditions. In addition to those options, we can instead choose to fix the subcooling in the system, and from there the charge will be calculated. On the high side, we can also choose to fix the condenser outlet temperature or the discharge pressure, and then the solver will work around this additional information to calculate the remaining details. Similarly, on the low side, instead of running the expansion device model, we can bypass it and fix the suction superheat, the evaporator outlet superheat, or the evaporator outlet quality. In many cases, the best option is to fix the subcooling and the superheat. This bypasses the expansion device model and allows the cycle to solve much more quickly. Beyond this, we have the adjustment parameters. These parameters are additional power sources that we can add to the system. So if we wanted to add an additional fixed power in the form of a parasitic power loss or an evaporator or condenser fan power, we can add those here. And these will be reflected in the total power consumption of the system, as well as the COP of the system. We can also apply a capacity loss, and this will directly subtract from the capacity that is calculated from the evaporator model. One important aspect of the system to choose is the refrigerant. So, by default, the refrigerant is R34A. There's a large number of refrigerants included. These all come from rough prop. If a refrigerant that you'd like to work with is not included here, you can add it as a user-defined mixture or a user-defined fluid file. And VapCyc will be able to run with that file. In addition to this, we give you the option of choosing the RefProp version you would like to run. There are minor differences between versions of RefProp, so we want to add this support in. We also add the option of running with the hybrid library, which can use curve fits to increase the speed of refrigerant property calculations. Another important aspect of the system to choose before running a simulation is the cycle context. This is basically the starting guess point for the solver. So during iterations, the solver will choose different suction and discharge saturation temperatures, and try to solve the system for the cycle convergence criteria that you set previously. And here in cycle context, you can set those initial guess values. So by default, it's set to be air conditioning conditions. You can also set it to be other application conditions, including heat pumping and low, medium, and high temperature refrigeration. And the suction temperature will change and discharge temperature will change to reflect that. You can also set user-defined values for these temperatures. Beyond this, we also have solver parameters that you can set. For the most part, it's okay to leave these as default. So that's the system parameters. So now I've gone over most of the basics of the system. In addition to choose component and edit component, when you right-click on a model, you can also add the same component in parallel, and that will copy your current component in parallel. And these, the mass flow rate were essentially split between these two components. You can also add a component in series. In addition to adding components in parallel and series, you can also add pipe models to the system. So if you right-click, you can choose Insert Pipe before component or after, and a pipe model will appear. The pipe model allows you to set inner diameter of a pipe and a length of pipe. So by default, this model basically is just a component that holds charge, essentially. But you can also have it exchange heat with the environment, so you can specify heat load or delta T. You can also have it be a pressure drop element, so you can apply a fixed value of pressure drop in the pipes, or use a valve type equation to calculate the pressure drop. You can also use correlations to calculate the pressure drop. So now to show off the Parametric Study feature, I'll open an example file. So also included in VapCyc install path are sample cycles you can use to get started with VapCyc. So here we have a cycle that has coil designer reader components for the condenser and the evaporator. It also has a map-based compressor model. And for the system parameters, we have a convergence criteria where we want the system to run, and have 15 degrees of subcooling and 20 degrees of superheat. So before we can run a parametric study, we have to run a successful simulation. For these cycles that are a bit more complex, there's a bit more iteration that's required for the simulation to solve, and during that iteration a window appears that shows a basic pH diagram while also showing the current residual. One aspect of the results that I didn't show previously is that you can export these results to Excel. So once you have a successful simulation, you can go to Results, Export to Excel, and a VapCyc results page will be generated in Excel. So there's one tab for each component, and the component results, and there's a tab for system state points and the overall system results here. So now that we have a simulation that is run successfully, we can do a parametric study on the system. So let's say that we wanted to evaluate the system at a range of different subcooling values. Let's say we wanted to see the effect of changing the subcooling of the system. This is the parametric study window. For now, we'll do an individual simulation, so we'll change one value in the system. Here in this drop-down, you can choose from all the available components in the system. You can also choose from the system convergence criteria. So I'll choose system property, and the available properties are the two convergence criteria, so I'll choose subcooling here. I'll select this as a parameter, and I'll vary the subcooling from 10 degrees F to a max value of 15 degrees F. And then I'll set the number of runs as 6. So now I can generate a table to simulate all of these values. We can also run these simulations in parallel. The number of parallel runs depends on how many cores you have on your computer. So running the parametric analysis, it'll take a couple seconds to set up, and then the simulations will run in parallel. Now we have successful simulation for all 6. And similar to the other results, we can export these to Excel. We can see bulk results for these different subcoolings. We can also look at plots for these simulations. So in this case, we have one X value, that's subcooling. We can look at the effect on COP, capacity, power consumption. Luckily, there's not much of an effect, so it's pretty consistent throughout. We can also do a multiplicative study. So in this case, we're going to look at all combinations of any parameters that we specify here. So here we can look at both the subcooling and the superheat. So we'll look at a superheat of between 20 and 30 and test the effect of that. Again, I'll do 6 here. You can update the table, and it'll be all combinations of these these range of variables that we've set here. And because it's 6 by 6, it's 36 simulations. So it'll take a few seconds to solve all of these. So all of our simulations have been completed. Now we can look at the plots, and we can look at the effect of superheat and subcooling on the CFP. So here, superheat had a negative effect on the CFP of the system. So that's a quick summary of the parametric analysis, and that concludes our quick demo of VapCyc. Thank you for watching. If you have any questions, feel free to send an email to our support email address for Optimized Thermal Systems, and we'll get back to you with an answer. Thanks.